हेलो एवरीवन, वेलकम टू क्लास 14 फॉर CFA लेवल 1 क्वांट्स। आज के क्लास में हम हमारा जो रीडिंग चल रहा था स्टैटिस्टिकल मेजर्स फॉर एसेट रिटर्न्स उसको कंटिन्यू करेंगे। और मैं बता दे रहा हूँ अब हम हमारे ये चैप्टर के ये रीडिंग के कंक्लूजन फेज में आ गए हैं। दो मेजर टॉपिक अपना बचा है, एक है स्क्यूनेस कर्टोसिस, एक है कोरिलेशन। ठीक है, दोनों ही बहुत इंपॉर्टेंट टॉपिक है। स्क्यूनेस कर्टोसिस तो चलो एक आइसोलेटेड टॉपिक है कि अगर आपने अभी किया और इसको खाली लेवल वन तक ही रखा और आप लेवल 2 लेवल 3 पे भी इसको कैरी नहीं कर रहे हो, मतलब इसका कोई खास फाउंडेशन नहीं बना रहे हो, तो अपने को चलेगा, अपने को कुछ खासा दिक्कत नहीं है। कोरिलेशन एक ऐसा चीज है जो आपको जिंदगी भर लेके चलना पड़ेगा, क्योंकि कोरिलेशन पोर्टफोलियो मैनेजमेंट में बहुत इंपॉर्टेंट रोल प्ले करता है। ठीक है, क्योंकि वो डाइवर्सिफिकेशन बेनिफिट एंड ऑल, वो पोर्टफोलियो में एक बहुत मेजर रोल, बहुत सिग्निफिकेंट रोल प्ले करता है। ठीक है, तो अपने को इंटेलिजेंटली समझना है। आज के क्लास में अपन सोलली स्क्यूनेस एंड कर्टोसिस करेंगे। ये दो अलग अलग टॉपिक है, दे आर नॉट द सेम टॉपिक, दे आर एक्चुअली डिस्टिंक्ट टॉपिक। एक साथ पढ़ाते हैं तो इसलिए उसको बोल देते हैं स्क्यूनेस और कर्टोसिस। तो अपने आज करेंगे ये वाला पेज। ठीक है, ये वाला करेंगे कर्टोसिस। ये करेंगे लेप्टोकार्टिक क्या होता है और आपका एक्सेस कर्टोसिस तक, यहां तक हम करेंगे। तो हम मोटा मोटा आज 2.5 पेज करने वाले। अगेन आज का क्लास में बहुत भरपूर एग्जाम्पल का डिस्कशन होगा, एकदम बेस से उठाया जाएगा। तो मिलते हैं अगला क्लास में। बाय गाइस।
So before we get into the concept of skewness, we will first see what is distribution, what do we mean by asymmetrical distribution, what do we mean by symmetrical distribution. Then we'll get into the details as to why do we need to read the concept of skewness, what is skewness, and then we'll move on to kurtosis, right? So distribution can be of two types. Now what the first question is, what is distribution, right? So distribution is primarily arrangement of data, right? So how well the data is distributed in the entire data set. So if I say that this is my population of data, then sorry. So if I say this is my population of data, then distribution would mean as to how my data is arranged, right? So if this is my entire population, so if I take an example of a city, right? So if this is the city, so there might be some area which is densely populated. There might be some area where the population is less, right? And there might be some area where we have medium range of population, that is somewhere between densely and less population, right? This happens in any of the city, right? So this is a very generic example that I'm taking so that you understand the distribution. So suppose, for example, if this entire city is of 200 square, if is of 2,000 square feet, and this is a 300 square feet place, whereas the less populated region is, for example, 400 square feet place, right? So if I make a statement that in a city, for example, the name of the city is A. In a city A, average population is around 20 per 100 square feet. Now, what does the statement would mean? This statement would mean that in the total city region, that is in the total region for the city, which is roughly around 2,000 square feet, in every 100 square feet you will find 20 people, right? So what would be the total population of the region? So the total population of the region would be 2,000 by 100 into 20, right? It is very simple mathematics, which is 400. So I can say that in my entire in my city A, average population is 20 in every 100 square feet, right? However, within the city, if you see, we have already taken an assumption that some are densely populated and some are less populated, right? And this is not an assumption, this is a reality. Although I'm taking a very small area, however, if you can compare any of the big cities like Mumbai, for example, Pune, for example, Bangalore or Kolkata, you will see that there would be some regions which are highly densely populated. There are other regions which are relatively less populated. However, from a city perspective, you will get a figure which will be between the most dense populated regions and the region which is less populated, right? So you can get somewhere in a number in between that, right? However, in the densely populated region, for example, the average is around 50 per 100 square feet, while in the less densely populated region, it can be 5 per 100 square feet. So what does it mean? So what does it indicate? So if I draw a line and take it as 20, if this is my average population, right? So you will find situations where I have a population which is more than 20. In the example we have taken as 50. However, you at the same time, you will find regions where the population is less than 50, which is 5. The example that we took, right? This is 5. Right? Further, there can be places, for example, this is very dense population, this is relatively less dense, then this is relatively less dense, this is the population density is very low. Over here, the population density may be a little more. So it can be like in some region the population density is 10. In some region the population density is 11. In some region the population density is 12. At the same time, in some region population density can be 25. In some region population density can be 26. It can be 30, right? So you can have different, even within a city, you can have different areas having different population density, right? So when we are taking a distribution of this city, the population distribution of the city, we will find that there are regions with different level of population density. Now this distribution, mark my words, I'm already using the word which I'm trying to define. This arrangement of the data. Now, what is this? This is ultimately a data, right? When you look at a statistician or when you are making some analysis, this is nothing. This is simply data that you are getting, right? You will work on these numbers. So these are data. So this arrangement of the population in different regions, different densities, this type of arrangement is only known as distribution, right? So what I'm trying to do is, rather than making you understand some theoretical concepts for distribution, giving you some nomenclature of statistics, I'm actually trying to make you understand distribution in a realistic sense, in a way you can connect with, right? For definitely for bookish definition, you can refer web. There are innumerable sources available, but that is not my objective in when I'm explaining you any concept. If I'm explaining any concept, the major objective that I have is that you understand that concept in details and actually correlate with what you're seeing in real life, right? That is only the main objective of study, that we understand, that we can actually, the things we are studying in our curriculum, we can actually understand and appreciate those things in real life. So it is because of that reason that I'm not taking any theoretical bookish definition. Rather, I'm taking a example which can be very clearly evident by you in terms of your day-to-day lives, right? So as we were discussing about distribution is nothing. Distribution means how the data is arranged. Distribution means how the data is arranged around the mean, around the average, whether it is very far away, whether it is near to the mean, how the data is moving, right? So that is known as distribution. Now distribution can be of two types. Now when we move into the types of distribution can be of two types, right? So distribution can be of two types: symmetrical distribution and asymmetrical distribution. Right, we will look into both of these in details. So for that, right. So now first we have already seen what is a distribution. Distribution means how the data is arranged. Now we will see what is symmetrical distribution and what is asymmetrical distribution, right? So what does symmetrical distribution says? A distribution is said to be symmetrical when it is shaped identical on both the sides. Now what is shaped identical on both the sides, right? The biggest question. So when we are taking a data, right? So suppose we have 50 data points in the entire population and we have to perform some statistical analysis on it. So how do we perform an analysis? How do we present it, right? So we have already seen the types of graph we make. So in order to be able to perform statistical procedure, what we do so in the distribution that we are discussing over here, so what we are doing, we are actually putting the data together and converting it into a bell curve. Why bell curve? Why are we creating this bell curve? The reason, as we will be moving further in the concept, you will be able to understand and appreciate the fact as to why are we making this bell curve. What is the significance of it? Because when we will be studying skewness, when we will be studying kurtosis, you will automatically get to know and automatically get to understand why is this bell curve required, right? For the time being, you assume that this distribution, just forget about symmetrical, asymmetrical. Just consider that this shape that we are making, the shape that we are making here is nothing. It is a representation. It is nothing but it is a graphical representation of your data with respect to certain statistical measures, right? So what I'm saying, the bell curve that we have made, you have to consider that, just forget about any symmetrical or asymmetrical. First you have to understand what is this bell curve, right? Because most of the books, when you start reading, they directly, rather than explaining what is a distribution and why are we taking, in order to understand the concept of skewness, kurtosis, in order to understand the distribution, why are we taking this bell curve, right? The one of the question when I was studying these concept is, why do we need a bell curve like this in order to represent distributions? So first you need to understand that why this bell curve. So before any asymmetrical or symmetrical, you consider that this is a graphical representation. So this bell curve is nothing. It is a graphical representation of your data. Now your data can be anything, right? We have taken multiple examples in the previous classes as well, where you have seen students marks scored by 40 students in a class in their exam, right? So even that data can also be represented in the form of a bell curve, right? So what are we considering? It is a graphical representation of your data with respect to certain statistical measures. Now what is this statistical measure? This statistical measure, in 95% of the situation, this statistical measure, when we are talking of a bell curve like this, when we are talking of a bell curve like this, when we are talking of a bell curve like this, in 95% of the situation, this statistical measure is nothing but mean of the data. That is arithmetic mean. Just one clarification that I wanted to give, because I received this question from one of the student on WhatsApp, is that he was asking as to when I'm using the term mean, what do I mean by the term mean? Whether it is an arithmetic mean, whether it is a geometric mean, whether it is an harmonic mean. So just to clarify on the fact is that whenever I am saying mean with respect to any of the data, the default assumption of that mean would be arithmetic mean, right? Whenever our objective is to use any mean other than arithmetic mean, so we have learned three types of mean, right? We have learned arithmetic mean, we have learned geometric mean, we have learned harmonic mean, right? However, when I'm using the term mean, my default assumption would be that I am I am talking about arithmetic mean, and that is the way you will find in any of the textbook, right? However, when I am intending to use any of the other types of mean, for example, geometric mean or harmonic mean, I will specifically specify, right? If I have to use these types of mean, I will specify that it is a geometric mean. I will specify that it is an harmonic mean. However, on places where I am using mean, it means arithmetic mean, right? It means arithmetic mean. So what is distribution? Distribution is symmetrical. What is distribution? Distribution primarily means the arrangement of the data as to how the data is arranged, right? What is symmetrical distribution? Symmetrical distribution is a type of distribution which is shaped identical on both the sides. Now, why this belt curve? What is this belt curve? This belt curve is nothing. It is a representation of data with respect to your statistical measure. That statistical measure is mean, right? Now we will look into the aspect of what is this bell curve, what does it mean, right? And what does statistical measure means over here, right? So if I copy it to other page, right? Now what did we discuss? A symmetrical distribution identical on both the sides. Right. So if you see the line that we had drawn, this line, if you see this distribution, the line that we are drawing over this side, this portion on the right, which I am marking with green, is exactly same with this portion which I am marking with blue. Right. So when your data can be presented in this manner, where two sides of the curve are exactly the same, then we say that your data has a symmetrical distribution. The distribution is symmetrical. Now the next question comes, what is this line that we are drawing, right? What does this line indicate? So this line, actually the point over here indicates mean. Just forget about this, that I have done this. Just forget about this portion. Forget for now. Let us first understand, right? So what are we trying to do, and what is this 1 and minus 1? So what are we trying to do is that we have a data set, right? Suppose we have a data set which has 10 data points. We will compute a mean around it. We will compute a mean, then we will compute a standard deviation. So I'm telling you the process as to how this type of bell-shaped curve comes, and how are we actually constructing it, and what do we mean by it, right? So suppose we have 10 data points. We will compute a mean around it. We will compute a standard deviation for it, right? The original data, right? The second I have mean, right? And the third I have standard deviation, right? So what, and if you see, if you remember my earlier classes where we had discussed about arithmetic mean, if this is my mean, And even when we were discussing about dispersion, if this is my mean, then I will have some observation which is above the mean, right? And some observation that will be below the mean, right? So we know that I have some observation which is above the mean, which will be actually positive, because when we were computing standard deviation, we did see this expression, right? We did see this expression. So what did we find? There were some observations which would give me this as positive, and there were some observations which would give me this as negative, right? So suppose rather than I draw a mean, I draw horizontal line for mean. Suppose I am drawing a vertical line for mean. Suppose here the mean was horizontal. Here the mean is vertical. Vertical, right? Now, we all have studied quadrants in our elementary school, right? We all have studied in our school. We have all have studied what is quadrant, right? What does quadrant means? What does y-axis means? What does x-axis means? So, just to remind you of the concept of quadrant, because I cannot take the risk of a student not understanding what is quadrant, because if he doesn't understand quadrant, then this concept will be difficult for him to catch. And if this concept is difficult for him to catch, then he will not be able to appreciate as to why we are studying skewness, why we are studying kurtosis, right? So that risk I cannot take. So if this is my y-axis and this is my x-axis, right? So if this is my y-axis and this is my x-axis, this will be a positive quadrant. So primarily what happens is that this is positive. In a axis, this is considered to be negative. This is considered to be positive. And this is considered to be negative. Right. So what do we understand with this? This will be a positive quadrant. This will be a negative positive quadrant, because whenever we are writing quadrant, we state the sign with respect to x-axis first and then the y-axis. So it is, the denotation is always x comma y. So whenever x is positive, you will see the positive sign in the first. Whenever x is negative, you will see the negative sign in first, right? In this, both are negative. And over here, x is positive and y is negative. So these are known as quadrants. Now suppose I draw a line of mean over here. Now back to the original, back to the concept that we had wanted to discuss. So rather than drawing a horizontal line as we were doing over here, rather than drawing a horizontal line, what I'm doing, I'm drawing a vertical line. Make sense? Now with respect to this vertical line, if we consider this vertical line to be a y-axis, right? We will have some data which is more than mean, and we will have some data which is less than mean, right? So in order to represent it, that some values are more than mean and some values are less than mean, what we'll consider, the values which are more than mean will be placed over here, right? The values which are less than mean will be placed over here, and mean will be in the center. So this is actually the starting point as to how we start constructing that bell-shaped curve, right? Now, when we say that the data is arranged in such a manner, I'll repeat my words. When I say that my data is distributed in such a manner that the values which are less than my mean is exactly in the same proportion with respect to the values that are more than mean. So what I'm basically trying to say is that if you consider it through if you consider it through an horizontal line, if I have a value which is positive by this magnitude, then I will, if the data is symmetrically distributed, then I will have a value which will be less than mean by the same magnitude. If my data is symmetrically distributed and nothing else. If my data is not symmetrically distributed, then this situation is not possible. Right? This is not possible if the data is not symmetrically distributed. So if the data is symmetrically distributed, then I will find that I will have some observations which is less than mean, and in the same proportion I will have some observation which is more than mean. And this region will be exactly same as this region. This is known as symmetrical distribution. This is known as symmetrical distribution. In essence, this is symmetrical distribution. So, and nothing else. If you could understand what the symmetrical distribution means, it is nothing. It simply means that when we are taking a mean, rather than taking it horizontally that we discussed in the previous class when we were discussing about dispersion, we take it vertically, right? We take the mean vertically, and you just think that if my data is symmetrical, then the data points on the right, just think in symmetrical distribution, if I have a mean, then the data points on the right will be in exactly same proportion as the data point on the left. You have to just think from that angle, that data point on the right is exactly same as data point on the left. If my distribution is symmetrical, right? If my distribution, I'm again repeating, if my distribution is symmetrical, then if I have a mean, then my data on the right of the mean will be same as that of data on the left. Right? Now, when you look at this example, this is an example of symmetrical distribution, right? One of the main feature of symmetrical distribution is that how will you know a distribution is symmetrical or not? So if the question comes, how do you know distribution is symmetrical or not? What will be your answer? You will definitely not construct a graph if you are given with suppose 50 100 data points, and if you are asked as to how do you know the data is symmetrical, you will definitely not construct a graph like this, right? The simple answer would be, if for the data my means is equal to my median is equal to my mode. So when we were discussing about measures of central tendency, we had individually gone into depths and details along with example as to how do we compute a simple arithmetic mean, how do we compute a median, how do we compute a mode, right? So if we are given with 50, 100 odd data points, and if we are asked to tell whether the distribution is symmetrical or not, our simple answer would be that I will compute three figures, I'll compute three measures, I'll compute a mean, I'll compute a median, and I'll compute a mode. If my mean is equal to my median is equal to my mode, I'll say my data is symmetrical. So one of the major feature of a symmetrical data is that the mean is equals to the median is equals to mode. Right. So how do we identify whether a data is symmetrical or not? A data is said to be symmetrical. A set of data, as in a population, is said to be symmetrical when the mean is equals to my median is equals to my mode. As simple as that. Right. Now, when you read through the chapters, you will also come across a term known as normal distribution. Right. But I don't want you to get confused from the term normal distribution, and don't think that normal distribution and symmetrical distribution are same, right? So what happens that since students don't study this concept in details and understanding the real meaning of the term, so these confusion usually persists that a normal distribution is symmetrical distribution. No, normal distribution is a type of symmetrical distribution. And in fact, the figure that I have drawn, this figure that I have drawn is more representative of a normal distribution itself, because when we will doing the further readings within Quants itself, we will be seeing in depth and in details the different types of distribution that exist. So there we will talk in details. As such, the entire chapter is majorly dedicated on these types of distribution itself. Right. So just to give a glimpse of it, the figure that I have drawn through which I am explaining symmetrical distribution is nothing. It is representative of normal distribution, right? And there are certain features of normal distribution, but symmetrical distribution and normal distribution are not same. Now, why are they not same, right? So, if I have to say, this is also symmetrical distribution. So, the figure was drawn very badly. So, I just want you to understand the essence. So, in the figure that I have drawn, this was a symmetrical distribution that I had explained to you, right? However, if you draw a figure like this, right? So both these figures, this one that I have earlier drawn and through which I am explaining you the concept of symmetrical distribution, as well as this one, both of them are symmetrical. Why? So if you could remember the definition of symmetrical distribution that we had studied, we had clearly called out that a symmetrical distribution is one which is identical on both sides of mean, right? Which is identical on both sides. By identical, you can actually use another synonym for identical is that it is a mirror image, and mirror image you will find in textbooks as well. Many of the textbooks, rather than using the word identical, they use the word mirror image. So if you see, these are mirror image of each other. So if you see the RHS is a mirror image of LHS. So both these distributions are symmetrical, but for a fact, this might be a normal distribution, but this is definitely not a normal distribution. So at least from this chapter point of view, you have to remember what is distribution, what are the different types of distribution. From types of distribution means symmetrical and asymmetrical. And third point that you need to remember is that a normal distribution is a type of symmetrical distribution, which means that if symmetrical distribution is a bigger set, then if this is the symmetrical distribution, Then within that we have a small subset which is known as normal distribution, which means that normal distributions are type of symmetrical distribution, but all symmetrical distributions are not normal. So normal distribution is a type of symmetrical distribution. Because I have seen 2-3 students having this confusion and asking to me over WhatsApp about this problem. It is because of that reason that I am taking this in detail, because if 2-3 students have a problem, then I believe that some of other students are also having a problem, that they get confused about what is a normal distribution, what is a standard normal distribution, how is it different from a symmetrical distribution, because the curve is actually bell shaped, right? So we get confused as to how do we distinguish between these type of curve, right? So in order to state in the smallest and in a summary form, normal distributions are type of symmetrical distribution, but not all symmetrical distribution, is a normal distribution. So at least from this reading point of view, remember this much. When we will be moving into the further reading, we will deep dive in detail as to each different types of distribution, and we will see what are the features. And there itself, you will have a very in-depth understanding of distributions, right? However, I had to make you understand different types of distribution. I had to make you understand what is a symmetrical distribution, what is a distribution, in order for you to understand the concept of skewness in a better manner, right? Now, what is a asymmetrical distribution? So we have seen what is a symmetrical distribution. If you just vice versa it, now what is vice versa it? So symmetrical was identical on both sides, right? Asymmetrical is simply a distribution which is not identical. Which is not identical on both sides, or both sides are not mirror image, right? So if you draw a distribution like this, where your mean would be somewhere around over here, right? Where your mean would be somewhere around over here. So if this is your mean, you can very well tell that this region is not identical to this region, right? This region is not identical to this, and neither they are mirror image of each other. So this is simply asymmetrical distribution. So having understood the concept of distribution, symmetrical and asymmetrical, now we will move on to skewness, and then you will be able to understand as to why I had discussed in details about these types of distribution, right? So we have already seen what is distribution, right? So for the last line, what does it say? For symmetrical distribution, interval of loss and gain will exhibit the same frequency. So we have already seen that we have some values more than mean, we have some values less than mean. So over here, when I am writing interval of loss or gain, so loss over here means less than mean, and gain over here would be more than mean, right? So that you have to interpret accordingly, because again in different textbook, the way it is expressed, the way distributions are expressed would be different, right? But the main concept is, and the crux of all the type of nomenclature, all the type of language that is used is, if your value is more than mean, then it will be on a positive side, then it will be a gain. If your value is less than mean, then it will be a loss, or it will be on a negative side, right? Now, what does skewness means? Skewness indicates. Now, what is a skewness first? Skewness is nothing, it is a measure. Like the measures of dispersion we have studied, right? We had studied 4-5 measures of dispersion. We had studied 3 measures of central tendency. Right? Simply skewness is nothing, it is a measure. Now, each and every measure we had discussed earlier, the 9-10 measures we had discussed, each of the measure would indicate something, right? The mean was showing the mid value. Median was showing the value which breaks the data into 2 equal halves. Mode was showing the value which is occurring most frequently in the data, right? So each of the measures, simply coefficient of variation was showing us the relative the relative dispersion of the data, right? It was a measure of relative dispersion. Similarly, downside deviation was showing us standard deviation with respect to where the observations were less than the where we had considered observations only which are less than the target, right? So each measure had separately indicated something. So skewness is also a measure which is indicating something. It indicates the extent to which a distribution is not symmetrical. So by computing a skewness, you can actually identify as to whether your data, as to by what extent your data is not symmetrical. So we had already discussed for a data in order to say that the data is symmetrical. We had already discussed, right? That if for a data my mean is equals to my median is equals to my mode, then I can say my data is symmetrical, right? So if they're not equal, then data is asymmetrical. Right? This is something that we know. If mean is equals to mode is equals to median, then my data is symmetrical. If they are not equal, then they are not symmetrical, means they are asymmetrical. But the next question comes, and here you need to understand the relevance of skewness. Although we know that my data is not symmetrical, my data is asymmetrical, but if I am asked to know the extent to which it is not symmetrical, the extent means to what degree my data is not identical, both halves of my data is not identical. I know by a simple calculation of this, I know that my data is not identical on both sides of mean, right? But if I now ask another question, a follow-up question, as to tell me the extent to which they are not matching, we need a measure to identify that extent, right? And that measure itself is known as skewness. So skewness here will not be used to tell whether the data is symmetrical or non-symmetrical. That is not the primary use of skewness. That is not the primary objective of skewness. You need to understand, right? Skewness, definitely skewness, when you compute a skewness, you will be, by solely and only computing skewness, you can tell that the data is symmetrical or not. But what I'm trying to say is that just to tell whether data is symmetrical or not symmetrical is not the key objective for computing skewness. But the key objective to compute skewness is to be able to tell that where the data is not symmetrical, to what extent it is not symmetrical. It will tell you the extent rather than giving you a simple black and white answer that it is symmetrical, it is not symmetrical. It will also play in that gray area where it will tell that, okay, my data is not symmetrical, but it is not symmetrical to this extent, right? So here the extent becomes my catchphrase. Right? Now, since it is a measure, so we know it can either be negative, it can be either positive. Now we will further see as to what does negative skewness means and what does positive skewness means and what does they indicate. Right? So skewness as a whole provides information about exceptionally high or exceptionally low values, right? So skewness will actually give you information about exceptionally high and exceptionally low values. Now, how will it give you such data, right? So suppose I give you an example. And for a fact, I know that I'm investing a lot of time in skewness, but my major objective for you is that you understand these concept of distribution, because these are actually the building block, right? Otherwise, I could have simply given 2-3 statement, had solved 2-3 sums, and embedded this in a very theoretical manner in your mind. But I actually want you to understand and feel the concept from inside. Then in that situation, you will not be required to read any text. If you just follow what I'm saying in class, and if you just able to visualize as to what I'm teaching, this concept will be permanently engraved in your mind, right? So if I take an example again of a data set where I have suppose observations like 30, 35, 36, 37, again 35, 32, 33. But at the same time, I have two numbers. So 1, 2, 3, 4, 5, 6, 7. Right. I have one number which is 100. Now suppose I have to compute a mean. Now my answer would be 30 plus, we have already seen how to compute mean, right? So I expect that you compute it along with me. So I expect that you are computing it along with me and not waiting for me to compute. I would suggest that you do this example with me so that you will be thorough with the concept itself. So it is 42.25. Right. Now what will I be doing? My x-axis, this is my mean. My mean is 42.25, right? This is my mean. I have some values which is less than 42.25. So it will be like 30. For example, 30, 32, 33, 32, 33. Then I have 35, 36, 37. Right. But I have one value which is 100. Right. Now if I try to draw bell-shaped curve over here, not exactly bell-shaped, if I try to draw a curve over here, I will find that I will have something like this. Right. Now suppose, in order to make our analysis better, if I hide this data in front of you, does understanding this graph tell me something? So if I'm thorough with my concept of skewness, what did skewness tell me? Skewness, one of the major objective was to indicate exceptionally high or low values, right? Now here in the example that we took, one of the major problem with respect to statistics when you're studying it theoretically is that with respect to the limitation in the number of data, here the data was 8, right? So because of that, because of the limitation in the number of data we had, you could have simply seen and told that, okay, we have an exceptionally high value over here, that is 100, which is actually having an influence on my mean, right? But suppose when this data is running into lakhs and lakhs of items, then individually seeing each of the number would be possible for you, right? And that is the play where statistics come into. Statistics is actually summarizing everything, because of which we can actually identify trends and patterns. So if you just imagine that this is not 8 data, this is rather 8 million data, right? These are 8 million data points, and through that 8 million data points, if we were able to compute this type of a graph, then will we be able to comment upon something when we know about skewness? Definitely, if you understand skewness well, you will see that this portion is actually indicating that in my data set, I have some values that are exceptionally high. Right. So once you study about skewness, you will be able to understand that definitely this is not a first. The first thing that you will see basis the graph that you have made is that first it is not symmetrical, right? So it is not symmetrical. So that symmetry portion is gone. This is asymmetrical. Now, once you have done, you have drawn this graph, you will be able to identify, okay, I have some exceptionally high data, I have some exceptionally large values in my data, which is actually pulling my mean. So what has this 100 over here has done? So if you see, my major concentration of data was around over here. So my major concentration of data was over here. So if you see, out of a population of, for example, 1,000 lakh, my major population was ranging over here, but I had one value which was over here. So what was the influence? It rather, if my mean could have been here, it pulled it to this place. My mean got skewed. My mean got skewed to the exceptionally high value. The impact of the exceptionally high value was that it pulled my mean towards it. What it has done, if this could have been my mean, had the exceptionally large value, if this could have been my mean, but what have this exceptionally large value did? It simply pulled the mean away from over here. Pulled. Similarly, when we have exceptionally small values, it will have the same effect. It will have an effect like my mean could have been here. My mean could have been here, but it pulled it to this point. So we'll have both right and left. We'll have similar impact both where the values are exceptionally high, but and the values are exceptionally low. But this is the kind of impact that this exceptionally large value did to my entire data set. Now, what the use of it? So, if you could remember, we had studied that when we have exceptionally large or exceptionally small values, rather than computing the mean, we compute two other measures. What was it? It was trimmed mean and it was Vinsored mean. So when the data is giving me a pattern like this, then I will actually move on to computing a Vinsored or a trimmed mean, right? So if you see that all the concepts are interrelated to each other, at that point you might not have been able to appreciate the fact as to why are we computing this Vinsored or trimmed mean. But after seeing this type of a situation where you have so much of data and you actually cannot identify any of the trend or pattern, once you start picturizing it, when you start computing it in a graph, you can actually see, you can actually identify trend or pattern, and accordingly you can then revise and adjust your measures, right? So we now see that skewness will give me data about exceptionally high and exceptionally low values. Now, how do we compute skewness? Now, this formula at one go might appear to be a bit tricky, a bit confusing, but once we will solve questions on this topic in later classes, you will see that the formula is very easy to handle, and most of the measures we have already computed, we had already seen. So the formula of skewness is xi minus x bar whole cube summation of them, right? So we already know what is xi. Xi is the individual observation. X bar, we also know it is the mean, right? We also know what is n. N is simply the total number of observation. At the same time, we also know what is SD. SD is the standard deviation. So the formula is summation of xi minus x bar cube by n into standard deviation cube. Now, why are we computing the cubes over here? Why are we not computing square, or why are we not taking the absolute values of xi minus x bar? So if you could see in one of the feature we had already discussed that it can be positive or it can be negative. It can be negative or it can be positive. Now, for it to be positive or negative, it is important that that the formula that we are using, the computation we are making, we ensure that the numbers are free to represent themselves. Because when we are using a modular sign, or when we are squaring, when we are using a modular sign or when we are squaring, we are actually forcing the numbers to be positive. So if you take a mod, then it will become positive. If you square it, then it will become again positive. But when you're cubing it, when you are taking the power of 3, then if you see, if it is a negative, if xi minus x bar summation is negative, then the cube will also be negative. At the same time, if this is positive, then the cube will also be positive. So what we have done, we have kept the originality of the deviation, right? Similarly, SD cube and N, right? For skewness, I have a major point to say that if you could remember my class on standard deviation, we had actually discussed separately what is the formula for population SD and what is the formula for sample SD. But for skewness, you have no such issues. You will have to simply compute the sample SD. You will have to simply compute the sample SD. Based on the sample SD and the total number of observation, you will get the denominator, and similarly you will get the numerator. So you don't have difference in formula between population skewness or sample skewness, right? Now, what does different number indicates? We'll get into that. Now, there can be 3 possibilities of this formula, right? So if you take this formula, there can be 3 possibilities out of it. One possibility that this entire skewness figure will become 0, right? The second possibility could be that it becomes positive. The third possibility is that it becomes negative, right? These are the primarily 3 possibilities. Now, what does that indicate? When skewness is positive, it means that the graph, the distribution would be right-tailed. And what is a right-tailed distribution? We will see just 5 minutes after the discussion is over. After this discussion formula for is over. Similarly, if the skewness is negative, the skewness is left-tailed. If it is positive, it would be right-tailed. If it is negative, the skewness figure, this figure that we have computed is negative, then it is left-tailed. If it is 0, then the data is 0 skewed. So what does it indicate? So if skewness is 0, it means that the distribution is symmetrical. So with the given data, rather than me computing mean, median, mode separately, if we simply compute skewness and the figure is 0, then also we can say that distribution is symmetrical. Now, what does right symmetry means? What does right tail mean, and what does left tail mean? So it is very, so even the name is very expressive of what we are trying to say. So we are just trying to say that positive skewness, right tail, this means that I have a tail on the right tailed, right skewed or right tailed, which means that my tail is moving towards right. So if you see the pattern, my tail is moving towards the right. Similarly, when I am telling you that it is left skewed or left tailed, my tail is moving towards the left. So you could actually identify that my tail is moving towards the right. Over here, my tail is moving towards the left. But how do we identify? So now suppose if I am given with 3 data, right? And the 3 data, and suppose if I am not given with any data points, if I am given with only 3 numbers, one is the mean, one is the median, one is the mode. And I have been asked 2 questions. First, identify whether it is symmetrical or not. So for identifying symmetrical, we will first see whether mean is equals to median is equals to mode. If not, then it is not symmetrical, right? The second question is, if not symmetrical, tell whether it is a right skewed data or it is a left skewed data. Then what will I do? How will I identify? So for telling whether a data is right skewed, or telling data is left skewed, we also have a relation between mean, median, and mode. So what does this relation states? It tells me that if the data is right skewed, that is moving towards right, if the data is right skewed, then my mean will be highest, followed by my median, and then my mode will be the least. So I request you to please write this relation in your notebooks. If you have taken a printout of the notes that I have shared in my Telegram channel, you can simply add this point over here, although it is mentioned over here. Because if you remember, when we were discussing about the mean, we were taking mean as the center point. All the values which were above mean were on the right. At the same time, all the values which were lower than mean. So if you could remember the example that we had taken over here. So if you could remember the example that we had taken over here, what we were saying is that all the values which were greater than the mean were on the right side, as well as all the values which are less than mean were on the left side, right? So if you similarly see this graph that has been presented, you will find that both mode and median are on the left of the mean, which indicates that mean and median would be, which means that median and mode would be less than mean. Now, what is the relation? Since we are going like this, which means that this value will be higher than this value, means A will be higher. Since we are moving on the left side, which means that A will be greater than B. So what we see, mean would be greater than median, and then median would be greater than mode. So if this relation persists, as in mean greater than median and then median greater than mode, then I will say that my data is right skewed. Further, if my relation speaks in a manner that my mean is the smallest, right? Then followed by if and median is greater than mean and the highest is the mode, because as we have already discussed, data which are towards the right of the mean are greater, right? So if this relation simply reverses and if this relation becomes mean less than median less than mode, then we will say that my data is left skewed. And this question actually comes in your exam. This question, you can be tested on this type of question where you are given three numbers, mean, median, and mode, and you are asked whether it is left skewed or right skewed. So it is because of that reason that I'm asking that please write both of this relation in your notebook, in your copy, anywhere where you can read and where you can actually remember that this relation exists between mean, median, and mode. Right. So with this, we have completed the concept of skewness in depth. Now we will be moving on to kurtosis. After having completed the concept of skewness, we will now move on to kurtosis. So in skewness, what we saw that whether the data is symmetrical or asymmetrical can be identified through the computation of skewness. And what does skewness means? What does it indicate, and what can it be used for, right? Now, skewness was primarily focused on the distribution of data, as to how the data is distributed. However, suppose if I need to identify and understand how closely my data points are around the mean, then the measure that I will be using is kurtosis. So if you see the definition of kurtosis, it states that it tells about the concentration. Now the catchphrase over here is the concentration. So kurtosis tells us about the concentration of the data around the mean, right? That is, provides a measure of the degree to which the distribution are more or less peak than normal distribution. So if you could remember earlier in the class, we had discussed about normal distribution, where I had told that students often confuse normal distribution with symmetrical distribution and are not able to understand the difference. But we had also discussed as to normal distribution is a type of symmetrical distribution with some other important features as well, which we will be discussing in the coming reading, right? So for now, with respect to kurtosis, we have to understand that what does kurtosis say, states. Kurtosis primarily provides us with a concentration, right? Concentration of what? Concentration of data. So kurtosis is telling us primarily the concentration of data. Concentration of data what? Primarily around the mean. right? So if you think of kurtosis, you need to primarily think as to if I'm having a mean. So if this is my mean, right? If this is my mean, I can have two situations I can have many situations. However, the primary two situation will be either my data is over here. If this is my worksheet to work on, my data can be over here. My positive datas. My positive datas can be over here. At the same time, my data can be over here. Because of which my mean comes over here, right? This can be one situation. However, in another situation, what can happen is that although my mean is same, but my data is concentrated like this. And my data is concentrated like this. And my mean is this. So if you see in both the situation, although we have the same mean, but it can happen that in one case, my data, my observations are far away from the mean, right? In the extreme ends, my data can be at the extreme ends. And in another case, I have with the same kind of a mean, with same amount of mean, my data or the observation are close to the mean, right? So among the various situations that can happen, these are the two extreme situations that I have discussed, right? Now, just by looking at the data, when we have thousands of data, right, and just by computing a mean out of it. So if I suppose this is the data, this is a population comprising of around 1 lakh data points. At the same time, again, this is the data comprising of around 1 lakh data points, right? And if I compute mean for both the datas, I'll definitely get that the mean is equal. Suppose we take a situation as such, right? Suppose mean is equal. Then with the same kind of mean, we will be able to comment that the mid value for all the observations together is the same for both the data, right? However, if we have to perform some other analysis, if we have to see how the data is bunched around the mean, if we have to understand that, then what we will be doing? In order to address that problem, we compute a measure known as kurtosis, right? So primarily in order to identify whether, so if we are given with a number mean and if we are given with two population set, then in order to identify how my data points behave around the mean, which means that whether it is near to the mean or it is far away from the mean. So let me repeat it again. When I am given mean of two data sets, and in order to identify as to how my data observations are behaving around the means as in whether the data is near the mean or whether the data is far away from the mean, in order to identify that, right? In order to identify that, we will compute kurtosis. Now the next question that you should ask is, why will I, as a person, why will I even bother to know whether the data is near to the mean or whether the data is far away from the mean? Now this question can actually be answered from the thought process of dispersion, right? So again, if I take an example where I state that so if I take an example where I'm stating that mean of data A, suppose data A and data B are two data is given to us. Mean for both the data is 10, right? However, if I have to make a sense, or suppose, let me just rub it. If suppose I have two investments, investment A and investment B, right? And suppose I am given with returns for past 100 years and returns for past 100 each, right? If I'm given this number. Further, if I get that the mean return comes out to be 10%. At the same time, in investment B as well, the mean return comes out to be 10%. Right? Then, how should I make the investment decision? How will I make an investment decision? What can be the criteria? Right? So if you remember my class on coefficient of variation, where we discussed about the measure of relative dispersion, what we mentioned is that we will compute the SD, right? We will compute SD. For example, SD over here comes out to be 8, SD over here comes out to be 9, and then we will compute coefficient of variation, right? And suppose if from coefficient of variation point of view, investment A has a lower CV and investment B has a higher CV, right? Then in that situation, and not suppose, since it is clear from the data that investment B will have a higher coefficient of variation. So if this is the situation, then as a rational person, the decision that I will make will be to invest in A, right? So I will invest in A, right? This is the basic thing that I will say after attending the class, right? However, if I now say that as a person, I need to get a general sense as to how this 10% has come, as in how the returns for past 100 years have been for investment A and investment B. Okay, we definitely know that investment A has a return of 10%, mean return of 10%, and investment B also has return of 10%, right? However, as a person, I would like not only want to understand their relative dispersion, but also I would like to understand that for the past 100 years, how has the return for each of the individual investment been around the mean? Which means that the question that I'm trying to ask, or the problem statement that I'm trying to address, is as to whether my returns for the past 100 years has been like 11%, 12%, or 9. It has been like 9%, 11%, 12%, 8%, or 9.5%, 11.5%, or maybe 7.5%, 12.5%. Whether the return has been in this pattern, or whether the return has been like 1%, 21%, 2%, 18%, 3%, maybe 15%, 5%, maybe in some other year I have received 25%. Whether my investment has been this irregular, or my investment has been regular. So what I'm trying to say is that once we have a mean, right, in order to have a sense of the data as to how the data is behaving around the mean. So we definitely know that mean is the central point, right? Mean is the midpoint. And we have already seen the computation of mean. Now, one peculiar thing, if you see with respect to mean, is that if you have two observations, only two observations, for example, 1 and 100, then in this situation, your mean will be 50.5, right? Again, in another instance, if your observations are 51 and 50, then also your mean will be 50.5. So if you see, even taking the extreme values and getting a mean value which is the same when we remove that extremities, right? So in order to understand the nature of the data, as to how the data is behaving, as to how when a mean is computing, how the data is behaving around the mean, In order to get a sense of that, we have introduced the concept of kurtosis. Now, this is very important. Even in the finance field, understanding kurtosis is very important for risk management, for appropriately being able to predict some event, appropriately able to understand how the investment will perform, what are the risks associated with investing in any asset class. So kurtosis is used for that purpose, because it will give you a sense as to, although your mean return is very high, for example, your mean return is as high as 20%, but when you draw kurtosis around it, you will identify as to whether that 20% is because of the fact that over the years I have received consistent returns of like 21, 19, 18, 22, or whether the 20% is due to some extreme gains in some year and some extreme loss in other, right? It can be either of the situation. So kurtosis gives you that behavior around the mean, right? Now, if you read the definition, I guess it will give you some clarity with respect to kurtosis. So we will be reading the definition again. So kurtosis is what we have earlier mentioned. Kurtosis is concentration of data primarily around the mean, right? What does it say? It tells us about the concentration of the data, right? That is, it provides a measure of the degree to which the distribution is more or less peak than normal distribution. Right. So if I take an example as to, right, suppose this is your normal distribution, right? We already know that normal distribution is a symmetrical distribution, right? So what we'll find, these two sides are identical to each other. Further, if you see, at this point, my data concentration is up to a certain extent. Now I will actually be using some layman terms to initially explain you the concept, and then when I be then I'll be introducing with the term. Suppose, for example, here I am saying that I am having a moderate concentration. So what do I mean by moderate concentration? Like, moderate concentration can be very broad, can be very vague term for you, right? So, but I don't want to currently name these terms now, because I believe that this only creates confusion with respect to every nomenclature, with respect to every term that we use. I'll be introducing it to you at the last, when we have been able to understand all the concept in a general manner, right? Now, with compared to my normal distribution, I can have multiple scenarios with respect to the behavior of my data, right? Now, however, primarily when we are understanding kurtosis, we take three situations, right? The first is the normal, distribution, right? The second, and apart from that, we have two more scenarios which we will be discussing now, and we will be seeing how the data, how depending upon how the data is behaving, what kind of conclusions can be derived, what are the types of insights that we can draw, right? So suppose this is my mean, right? Now, I totally agree on the fact that there can be various scenarios, but from understanding, because definitely performing an analysis, understanding the data has its own limitation with respect to time and cost, right? So you cannot always go on analyzing everything, each and every trend. You have to make certain assumptions. You will have to drill down upon something. You will have to summarize things, right? So for that purpose, when we are talking about kurtosis, we primarily talk about three situations, right? The first is a normal distribution that we are saying. The second situation that we are discussing is where now what does this mean? If you could see, if this is my mean, over here, if you see, the concentration of observation around this mean point concentration of observation around this mean point, concentration of observation around it is medium. And definitely when I'm using the word medium, I actually do not mean it is medium, but I don't want to actually use technical terms now, because I don't want you to focus currently on the technicalities. I just want you to understand and grab the concept. Believe me, we will be learning each and every term, we will be understanding in each and every term even before we know the term, right? So just have a bit of patience with me. When I'm using this term, I'm using it in a very layman terms, and this is just for you to be able to absorb the content in a better manner, right? So over here, what we see, the concentration of observation is medium. However, in the other situation, what we are seeing, if you see, the concentration of data around the median is very high. Right. At the same time, if we take a third scenario, over here, if you see, the concentration of data is low, relatively low, right? So if you think from your common sense point of view, so if you think from the common sense point of view, there can only be three possible situations, right? With respect to data concentration around the mean. It can either be high, it can either be medium, it can either be low. And what we have done, irrespective of n number of situations, irrespective of n number of behavior that a data can show with respect to its mean, we have actually bucketed all of them into three categories. One is high, concentration is high around the median, concentration is high around the mean, concentration is medium around the mean, and concentration is low. So what we have done, we have primarily bucketed, right? Now over here, right now with this, we have understood how the data behaves, what does kurtosis believes, what does kurtosis actually indicates, how the data is behaving, and how are we bucketing it. Now we will move into the technical words of the concept which we have seen over here, right? So now we go on to the kurtosis page. So we have already seen what does kurtosis means. Kurtosis means concentration of the data. What does kurtosis means? Kurtosis means concentration. Why? Of what? Whether it is more or less. So I have used the word more or less. More means high, less means low. And here normal distribution would indicate medium. Right. Kurtosis is primarily of three types. So not kurtosis, but any type of data can actually be categorized into three types of kurtosis data, right? The first one is the leptokurtic, the second is the mesokurtic, and the third is the platykurtic. Now what does it mean? So to begin with, we'll begin with mesokurtic. As you can see, mesokurtic data, a normal distribution is known as a mesokurtic data. So here you need to be very careful in terms. Here I have mentioned normal distribution and not symmetrical distribution. Again, over here, many students have confusion. So I want to make it very clear. When I am telling a mesokurtic data, I mean normal distribution and not symmetrical distribution. So what we had studied, if symmetrical distribution is a larger set, then normal distribution is a subset of it. So what we are trying to cover is the subset. So this subset is the mesokurtic data. Right. So when we are talking of a normal distribution, we can also call it as a mesokurtic data. right? This is the nomenclature that is given. Now, if you could see the expression of kurtosis, so similar to the formula of skewness, we have a formula for kurtosis as well. So in skewness, we used to write skewness equals to this, right? However, for kurtosis, we have an expression for kurtosis. For example, like mean. Mean we can show as this, right? We do show mean as this. We do show mean as this, mu. Similarly, we do show standard deviation as sigma, right? So similarly, kurtosis is indicated or denoted by the word K. So a mesokartic data also, which is a normal distribution, the K value is always 3 and it is a given value. So if you are given that you have a normal distribution and tell the kurtosis value of that distribution, the answer would be 3. Because it is given that normal distribution will have a kurtosis value of 3. And why given, we will be discussing it in the coming discussion that we will do, right? So mesokartic data will have a kurtosis of 3, right? The remaining two, among the remaining two, we'll first see the leptokartic. So what is a leptokartic data? First thing, the leptokartic data is a data where the kurtosis is greater than 3, right? So when we are computing kurtosis of any data, if its K value is greater than 3, so when we are computing kurtosis of any data, see, when we are computing kurtosis of any data, we can have majorly 3 situations, right? One, the kurtosis will be 3. Second, the kurtosis will be greater than 3. Third, the kurtosis will be lower than 3, right? If you think when we are computing a kurtosis value of any data, right, there can be 3 possibilities. One, the kurtosis is equal to a number. Second, it is greater than that number. And the third, it is lower than that number, right? There cannot be any fourth option. So we have already seen the nomenclature that we use when kurtosis value is 3. So when kurtosis is 3, the data is said to be mesokartic, right? Similarly, when we compute the kurtosis value, right? And just one point that I want to make when I'm telling kurtosis value, please don't think that what will be the formula. We will read each and everything, right? You just stay with me in the discussion and we will slowly cover each and everything around the concept as well, right? So first, we have seen with respect to kurtosis, we have seen that kurtosis, we can compute kurtosis value through a formula. We have seen 3 situations with respect to kurtosis. One where the kurtosis value is 3. Second, where the kurtosis value is greater than 3. Third, where the kurtosis value is less than 3, right? When the kurtosis value is 3, we will say that it is a normal distribution or it is a mesokartic data, right? Second situation, which we are discussing currently, is leptokartic. What is leptokartic? Leptokartic is a situation where the kurtosis value for the data comes out to be greater than 3. So for any data where the kurtosis value is greater than 3, I will say it is leptokartic. The third situation which we are discussing is the platykartic data, right? So we have already seen when the K is equal to 3, K is greater than 3. So the last option left is K is less than 3. So when K is less than 3, I call the data as platykartic. Right? Now what does it indicate? So if you see the data over here, right? If you see the data over here, this graph that I have drawn is actually the graph for leptokartic data. And if you could identify the similarity between this graph and the graph that we had seen in the example, what we discussed, this graph indicates nothing but the concentration of data is higher around the mean. Right, if you could remember. At the same time, this data that I have drawn over here is known as platykartic data. And if you could remember, we had also discussed that the concentration of data around the mean is lower. And again, the concentration of data around this normal distribution is medium. So now you can understand why was I using the term high, medium, and low. I wanted to indicate that when I'm telling high, it means high would indicate k greater than 3, medium would indicate k is equals to 3, and low would indicate k less than 3, right? So when I was using the word high, medium, and low, I meant with respect to k. So now when you try to read this concept, when you try to understand this concept, you can remember it in a manner that I have three bucketing of my data: high, medium, low. Now again, I have to correlate it with the concept of kurtosis. So for high, my k will be greater than 3. For medium, my k is equal to 3, and for lower, my k is less than 3. Right? Now, what does this data? What does this leptocartic, mesocartic, and platycartic data indicate? Right? So first, we will see the leptocartic data, and basis the leptocartic data, we will understand the remaining two type of data as well. So when we are talking of a leptocartic data distribution, we say that more returns are around the mean, which is similar to what we have seen. So leptocartic data indicates that we have more return around the mean. However, we have one more dynamic over here. If you could see the distribution, we not only had more returns around the mean. If you could see the distribution, we not only had more returns around the mean, we also had more observation at its tails. So the distribution actually flows like, so over here you have higher values, higher number of observation. At the same time over here you have higher number of observations, right? So we have more number of returns around the mean. At the same time we have more returns far from the mean. So there are two extreme situations happening, right? We have observations which are close to mean, and we have observations which are far away from mean. So if you would want to visualize it using a horizontal line, so this is my total data set and this is my mean, right? So we have situation where I have data around over here, and I have data over here. Whereas this portion which I am marking in purple is somewhere less dense, means I have very few observation in this purple portion, which means that I have observations which are very close to mean, as well as I have observation which is very far away from mean, but I don't have observation which is in between that, between this length, that is close to mean and far away, right? Now what does this indicate? Now the interpretation of this is very nice, right? And you should understand it very properly. Now what it is indicating? It is actually indicating greater risk. Greater risk, by risk, can you imagine something that we had already discussed in the previous classes? By risk, what do I mean? What does risk indicate? We have already studied, right? What does risk indicate? Risk is actually dispersion. Risk is actually the measure of dispersion which we were discussing. Right. Now just remember the earlier example that I took with respect to investment A and B. So what I was telling with respect to investment A and B, where we had seen that coefficient of variation for investment B for higher, which meant that B was a riskier asset. However, what I was trying to say is that, and at the same time, when I diverted that discussion of coefficient of variation to kurtosis, what did I say? I definitely mentioned the fact that when the person wants to understand the behavior of returns of investment B over the 100 years, then he will draw a graph. Then he will identify kurtosis. But one thing that remained constant was the outcome, was the insights that we draw from that coefficient of variation and kurtosis. The insights were same, right? What were the insights? Even when we use the measure of dispersion, you will get an insight with respect to the risk, right? Those measures of dispersion will give you an insight of risk. At the same time, kurtosis will also give you insights of risk. So here, the ultimate insight, the ultimate goal that you want to achieve is the understanding of risk for a data. But the type of insight that they will be giving will be different. And that is why we have these two different measures. Now again, how do we compute it? What is the formula? Which is the major question by now, I believe. So the formula for kurtosis is very similar to the formula for skewness, if you could remember. In skewness, we had xi minus x bar whole cube by n into sd cube. However, over here, I have, instead of cube, I have to the power 4. Just simple as that. No further discussion needed. All discussion that we had during the formula of skewness holds same for kurtosis, except of the fact that instead of cube, we have to the power 4 for kurtosis. That's it. Right. Now, within kurtosis, we have one more concept known as excess kurtosis. Now, what is excess kurtosis? So, if you have seen the different type of kurtosis that we had discussed, mesokartic, leptokartic, and platykartic, what we had seen is that we were describing the data basis whether the kurtosis is more than 3, 3 or less than 3, right? So here 3 was the base number that we were taking. Usually what happens when we are talking of negatives and positives, if a number is greater than 0, it is called as positive. If a number is less than 0, it is called as negative, right? When we are talking about positives and negatives. But when we are talking about kurtosis in the situation such as platykartic, leptokartic, and mesokartic, the base number that we were taking was 3, right? So because we were taking a base number as 3, we find that in order to define the concept of excess kurtosis, we are saying that the data has excess kurtosis. The data exhibits excess kurtosis if it is either greater than 3 or less than 3. Now, what does this mean? If it means that if k is equals to 3, data has no excess kurtosis. Simple as that. Now, based on suppose now after having done this, if I tell you a question, if I ask a question from you, that suppose my excess kurtosis is -1. Please hear to the question very properly, right? Because these type of question, you can actually be tested on these types of questions. So if the question is, suppose your excess kurtosis is -1, tell me the nature of the data, whether it is leptokartic, whether it is platykartic, whether it is mesokartic. How will you identify it? So what is the question? The question is, suppose excess kurtosis like EK is equals to -1. Identify the type of data. Right. What will it be? Now, if you remember, the formula for excess kurtosis was k minus 3. Excess kurtosis over here is -1. So, k will be equal to 3 minus 1, which is 2. K will be 2. Now, we have seen three things, right? K greater than 3, k equal to 3, k less than 3. K greater than 3 was leptokartic, means more risk. Mesokartic and platykartic. Here the k value comes out to be 2, which is less than 3, which means that it is platykartic data. Based on same logic, if k was, for example, 2, then in that situation, k would have been 5 and the answer would have been leptokartic. Right. So through the help of excess kurtosis, you can actually identify whether the data is mesokartic, whether the data is leptokartic, or whether the data is, similarly, if EK was 3, if EK was 0, then we could say that over here, and then k is equal to 0, the data is mesokartic. So based on what is the value of your excess kurtosis, you can identify whether the data is leptokartic, whether the data is platykartic, or whether the data is mesokartic. And over here, if you observe, this is the only thing that I have mentioned. Right. Excess kurtosis, kurtosis minus 3. Now, in the bracket, if you see what I have discussed, if it is positive, means if excess kurtosis is positive, the data is leptokartic. The example that we took, where excess kurtosis was 2, in that situation, your kurtosis is 5. Kurtosis greater than 3 was leptokartic. Similarly, where we took an example where excess kurtosis was minus 1, in that situation, kurtosis was coming out to be 2. That is kurtosis less than 3, which means that data is platykartic. Alright. So with this, we covered the discussion of kurtosis as well.